In this video, I'm going to give just the briefest of overviews about some of the non-organic sorts of elements that we're going to be encountering in biochemistry. And my original plan for this was that I was going to go into a lot more detail. I was going to maybe talk about things like molecular orbital theory and then crystal field theory and ligand field theory and TS diagrams and all that, but there is just way too much background there for a playlist that is on biochemistry, and most of that really doesn't come into play for the biochemistry that I'm going to talk about. And besides, that's probably where my quantum mechanics playlist will eventually go once I get into things like atomic orbital theory, and then I can start getting into the group theory and things like that. And but anyway, in this video, I'm going to talk mostly about ionization energy. So ionization energy. I'm going to talk about solubility a little bit, solubility, and I'm going to talk about coordination, or complex chemistry. And once again, this is going to be just sort of the briefest of overviews of these things. And so here I just have the ionization energy. So this is a periodic table with the ionization energies well, the first ionization energies of all these atoms here. And this one, which shows sort of the ionization energy trend, where these ones over here, except for hydrogen, that are low, these do not have these have really low ionization energy, and so they ionize quite easily. In fact, these ones on the far left here, these actually ionize. They want to give away their electrons so readily that if they're exposed to air or water, they will actually burn because they're giving away their electrons so quickly or so readily. Quickly would be sort of a kinetic statement, where readily, I guess, is sort of a thermodynamic statement. And then if we look over here on this side, it's sort of the opposite, where these ones want to steal electrons really fast. And so these are oxidizing agents. And we see that oxygen here and nitrogen and fluorine are all very oxidative. I mean, these ones on the very far right of it are even more so, but those are like the noble gases. We essentially just pretend that those ones just, just always have electrons. Those are inert, essentially. But we see that these ones here, like the oxygen and nitrogen, fluorine, which do not always have a full 8 electrons in their valence shell, are going to be stealing electrons quite easily. And in fact, so readily, oxygen, is causes oxidative stress because we breathe it in. Fluorine, you can't even let it touch air because it'll just burn because it steals electrons so easily. But anyway, when we're talking about ions in organic chemistry, or biochemistry rather, so a lot of the ones we're going to be talking about are like the sodium, the potassium, the magnesium, the calcium, things like manganese, iron, zinc, copper. So a lot of those ones, and we see that those things. So pretty much, if as we go this way, these red ones and blue ones are all going to lose electrons and become positively charged. All right, and down here, I'm actually going to zoom in a little bit to see it better. So this is just some periodic trends where once again we see this ionization energy increases as we go from left to right across the periodic table and as we go from top to bottom on the periodic table. And I mean, you could think of electron affinity as sort of the same thing because something that has more electron affinity, you're going to need more energy to actually ionize it. Uh, and down here, we also see this non-metallic character, metallic character. Uh, and in a way, those are sort of this, have the same trend as this ionization energy because metallic character is, I mean, you could probably think about it as like conductivity. And so, I mean, that's probably maybe not a good way to talk about it, but it does have to do with sort of the way that electrons are conducted. And so we see atomic radius once again uh, increases as we go this way, and that actually has to do with that electron affinity. So as we go across this way, we are increasing the positive charge in our nucleus. And so that's going to sort of pull the electrons in more. And so it makes the atomic radius reduce as we go this way across the periodic table. So the next thing I wanted to talk about was solubility. And so when something dissolves in water, it essentially does what I have pictured right here. So the partial negative charges on these water molecules here. So this red is the oxygen. These white ones here are the hydrogen. So that's H2O. Sort of surround this positively charged ion here. So this Na is sodium. And you'd see the opposite if you had, say, a chloride ion, which is negative. You would have the hydrogens going towards it like this. And so we'd have a bunch of the partial positives on the hydrogens surrounding the negative charge. And so that helps neutralize the charge on it. And so when we are thinking about solubility, we want this KSP, which is the solubility constant. And so that's equal to the concentration of, say, well, actually I have this down here, the Mg and Cl2 going to Mg2 plus and then 2 Cl minuses. So in chemistry, when you have square brackets like that, that usually denotes concentration. And so we have the concentration of each of these, the magnesium and the chloride, and then we raise it to the power of this coefficient here. And so we see that if we have A with a little x, some chemical A and then some chemical B that has that many in this ionic compound, we end up with that many A's and that many B's. And so we have the concentration of A and the concentration of B raised to the power of their coefficients. And so I actually found this for the solubility of magnesium chloride here. This solubility probably makes a little bit more sense. When it talks about the solubility, that's sort of the maximum solubility. That's, you can put this many grams of magnesium chloride into 1 liter of water before it starts getting oversaturated. And so when it starts getting oversaturated, so you have your container here of water. When it's oversaturated, you'll start getting solid building up within your liquid there. So if you've ever, taken like a little glass of water and dumped a bunch of salt in it, There's a certain amount of salt you can put into the water where it's going to dissolve in the water, but at a certain point it's going to start building up on the bottom. And so this solubility is telling you how much you can put in before it starts building up on the bottom. And this KSP has to do with solutions or concentrations, rather, usually as molar concentrations. So that would be like moles per liter. That's what these concentrations would be. So this would be concentration as a mole per liter. And so this KSP would actually, well, I'm not going to go into units on this, but anyway, so you can also have things that have multiple sort of solubility, and this is actually a sort of special kind of solubility here that has to do with these hydrogen ions rather than things like magnesium ions or sodium ions. These H plus ions are what are called Bronsted-Lowry acids. And so this is actually a sort of pH thing where pH is sort of a, I guess, special case of this solubility that just has to do with these Bronsted-Lowry. So we'll call that BL, Bronsted-Lowry acids. And so this has this H3PO4 has 3 H's on it. And so it can actually lose one of them, it can lose two of them, or it can lose all three of them. And those will actually have different solubilities. So this Ka is actually the solubility constant, and then P means we're taking the negative logarithm of it. And so when this number is low, that means it has a high, that means it wants to give that hydrogen away more strongly. And so as these numbers increase, it's giving away those hydrogens less and less. And so we can see if we, go to this right here, H2PO4, and then one H plus here, that's going to happen quite readily. But as we keep increasing the charge on here, it's going to happen less and less readily. And it would also be increasing the pH of water. So pH is kind of the same thing where this P just means we are taking the negative logarithm, and the H means we're taking the negative logarithm of the hydrogen, of these hydrogen plus ions. So the negative logarithm of the concentration of those there. And so that's just a little bit of solubility and sort of how things dissolve in water. So down here, this is just called the Nernst equation. So it's the Nernst equation, and it's sort of a generalization of sort of an equation where we're talking about if we have like a semi-permeable membrane, like say a cell membrane here, and we have some concentration of Na plus Cl minus over here, so that dissolved in here, and Na plus Cl minus, and I'll even put concentration here because we're talking about concentrations. Then it's going to create some charge across this membrane, or some potential is actually more accurately. I mean, each of these things is charged. We're creating a potential across this membrane. And so what we see here is our positive ions on the outside. So I'll put a red here, and we'll call this over here outside. So this is out, and this is in. Inside and outside our membrane here. And so we have this red here for the positive ions outside, so that's right here. And then I'll use orange here for the negative ions on the inside. and then I'll use green for the positive ions on the inside, and then blue here for the negative ions on the outside. And that makes sense because if we're talking about sort of uh, the the positive ions outside and negative ions inside, those are going to, or the positive ions outside and the negative ions outside, we see that one of those is in the denominator and the other is in the numerator here. And that makes sense because those are two things are going to have a different effect on this potential across the membrane. And same for with the positive ions on the inside here, and then the negative ions on the inside here are going to have a different effect on that potential, because a potential is essentially just a change, just a difference in charge. And so if we say had more positive ions on the outside here, that would be the same as having more negative ions on the inside here. Either way, there would be a difference of positive and negative between the outside and inside. And so this is something that we're going to run into as we go through biochemistry, these different concentrations of ions on different sides of this membrane here. And that's important for things like absorption in the intestines. It's important for things like action potentials in neurons and muscles and heart tissue and things like that. And so yeah, so the other things to notice, one of the other things to notice is that this is affected by temperature. And so, obviously when we're working in the body, we'll be working with temperatures that are body temperature, which is 98.6 degrees Fahrenheit or 37 degrees Celsius, which, so what would that be, Kelvin? Because I think yeah, it's usually in kelvins. I forget offhand, so I think 0 degrees Celsius is equal to, I believe it's 273 Kelvin. So it would just be this plus 37. But anyway, let's not get too bogged down in that. So this is pretty much, well, actually, forgot about this. So this has to do with more of that stuff I said I was going to skip over, but I'm going to give just a really quick thing here. So this has to do with complex and coordination chemistry, and it just has to do with when we have a metal ion, which is what this M is here, we can have it coordinate between a bunch of different things. So this right here is, and you may have seen this as an ingredient in some things. It's called EDTA, or ethylene diamine tetraacetic acid. So ethylene is this, diamine and tetra, 1, 2, 3, 4 tetraacetic acid. And this is what is called a polydentate complex. And dentate, coming from the same root as teeth, like the orthodontist or the dentist or things like that. And it's just saying, it's essentially thinking of these things binding to the metal ion as teeth. Like this is a mouth sort of biting down on this metal ion. And so there are multiple of them, and so it is polydentate. So this table here is a bunch of mono, so single dentate here. And so we see that these are the what are called ligands here on the left side of the table. So OH, which is just an oxygen with a negative charge bound to a single hydrogen. This negative charge will want to, if we have some metal here, it will complex with that metal. And so we also have this ammonia here, which that's actually like this. It has three H's on it. Then it has this lone pair of electrons here, uh, which will also complex with the metal. And then we also have this CO3 here, which is CO double bond like that, negative and negative, and those will bind to metal ions. And this is just looking at when they bind to either iron in the 2 plus state, the 3 plus state, or cobalt, or copper, or aluminum, or chromium. It actually turns the solutions into these colors. So the colors that we see on the table here. And that gets into that stuff about what I was talking about earlier with the ligand field theory and that kind of stuff. So I'm not going to go too deeply into all that because that is a huge rabbit hole. But the idea is just that when you have these different things coordinating with your metal ion, it changes the way that light interacts with the metal ion. And so it actually changes the color of the solution. And so, yeah, this is just, kind of a small table. So, a lot of the things we'll be looking at in biochemistry will be more things that look like these polydentate ions, because a lot of what we'll be seeing is, some metal ion here, bound inside of a protein. So the protein will have residues coming in and coordinating with our metal. And if you've watched my videos on the biosynthesis of all the different vitamins and stuff already, you will have already seen this, where we have, things like magnesium ions coordinated inside the proteins. We've seen zinc ions coordinated. We have seen iron ions, so 2 plus, and iron 3 plus. And so, yeah, we've encountered all of these things. So these magnesiums will be coordinated in there, usually with, some kind of acid, or deprotonated acid. Same with the zinc. The iron are often in there with so that there's a sulfur here. So these cysteines like this, and we've also seen the like iron sulfur sort of like sort of things that look like this, where we are making these sort of boxes of these things. I'm not going to draw the whole thing, but so these iron and sulfur compounds like this. But anyway, this is all just a little bit of stuff about some of the minerals, some of the electrolytes and things like that we will be encountering in our biochemistry. And like I said, we've already encountered a lot of this stuff. Um, you know, this is, I guess a little bit all a little bit late. I mean, I've talked about this a little bit in my general chemistry playlist as well. So if you're not familiar with some of these concepts, that would probably be a good place to go to get more background information. But starting in the next video, in this nutrition and metabolism playlist, I will be talking about I'll be talking about the actual, human metabolism and nutrition and things like that. So we'll finally be getting past all this prelude stuff into the actual meat of the nutrition and metabolism playlist. But anyway, I hope you found this at least, somewhat of an introduction to this topic. Uh, so yeah, anyway, I will see you in the next video.